Okay, so good morning, good afternoon, and good evening, everyone, as always. So very nice to see you people. This is our third day of Women in Astronomy Working Group Training Program. And for today, we again have the same session like on the first day, but the new part or the other part added to it. That is the sun available for everyone, exploring solar images with a visualization software. And today's coordinator is Santiago Vargas Dominguez from Colombia. And he is going to explain us today a bit more advanced tools to look at solar images. So I will hand over to Santiago from this, and he's going to conduct the training program for today. Santiago.
Okay, perfect. Thank you very much. So thanks for joining this second session of my part, which is talking about how to explore solar images. In the first session, we were looking at some possibilities to look at the images taken from solar telescopes, basically space-based solar telescopes. So we have a long list of solar telescopes available at the moment, and we are waiting for the new generation. Well, actually, we have already 2 satellites, solar missions, which are part of the new generation of solar telescopes. But also there are some plans for the next generation that will be probably launched in about 4 years from now, 5 years from now. So welcome for the ones who were in the first session, and also for others that might be joining today. So I will try to explain a little bit very fast what we did last time. Basically, I started by presenting some of the images and videos that we have already available. And this is very inspiring because this is the first time we are able to look at the sun with these capabilities, with this high resolution, temporal and spatial resolution. And this is something amazing because we evidence how the sun evolves, how dynamic our star is, and also all the interplay between the plasma and the magnetic field, which is basically the process behind all this that you're looking at in this video. So actually these videos are available in YouTube. You can just type, for example, Solar Dynamics Observatory, which is the telescope that since 2010 is giving some of the best time series of images of the sun, our sun. Okay, so also I mentioned this spaceweather.com website, which is being updated every day, actually many times per day also. So if you want, we can start by looking at this space weather website for today. So we can just type space weather in Google, and here you have, going to enlarge a little bit this because I'm sharing my whole desktop, so I'm moving around from different applications. So basically for today's information, we have the conditions, the current conditions, once again, of the space weather in terms of the solar wind. This is the speed of the solar wind, almost 400 kilometers per second. You have the density of protons per volume in centimeters. And also you have the information about solar flares. So flaring activity is what we call the activity of the sun, which is characterized by the energy release. So you have different types of flares. Actually, in the Slack channel, someone asked me about the C6 type. And basically, I'm going to show you in a moment all different types of flares that you can describe in the sun. Okay, what else? You have always many information about the aurora, because there are many people waiting for auroras to happen so that they can plan aurora tours. And basically you have available many different places in North Europe, but also in Canada, and that's for the what we call northern lights, but also you have to know that in the south we also have auroras, but because there are many, less locations and less towns, probably they are less known than the northern lights in the northern part of the planet. Okay, we have the daily sun, which is thumbnail of the solar disk with all different regions that are appearing in the solar surface. So basically, this is what we call active regions, and they have a number, so a consecutive numbering, which is telling how these active regions start to grow from day to day, or they can also disappear. So we can have a variation, intense variation of active regions from one day to the next day or the next week or the next month. And this is basically what we are looking at here. This is the solar cycle. Well, the beginning of the solar cycle number 25, which is the one we are right now. This is real data, all the variations in the number of sunspots in the sun, in the solar surface, basically what we call the photosphere, which is the one we are looking at here. This is visible light, or what we also call continuum or white light. And this is the number of active regions. So basically this data is showing December last year, so a month ago, well, a few weeks ago, as the last data available. But if we go to the red line, this is telling something that what we can predict. So there are different forecasts for how the solar cycle is going to behave, the current solar cycle number 25. And as you notice from this plot, the predictions are a bit, well, they have started to be a bit different from the actual data. So apparently the solar cycle is rising up faster than we predicted. Well, I have to say that there is not only one prediction, but you can find different predictions. But anyhow, this is showing also how difficult it is to predict how the sun is going to behave, how the activity of the sun is going to be like in the next year or the next few years ahead. Remember that the solar cycle in principle has roughly 11 years of period. So this is from the minimum here to the next one is more or less 11, 12 years. And this is something that was discovered already more than 100 years ago in the mid 19th century. But somehow the sun is behaving like that since then. So let me actually go to the complete picture here, because this is solar cycle number 25. Again, this is the one we are living right now. And the previous one, solar cycle number 24, which is this one. You have the real data, and this is a fit. This is like an average, the blue or purple line. So somehow the predictions are telling that this solar cycle is going to be quite about the same as the previous one. But according to the data, which has been acquired in the last month, since almost a year ago, this increment is steeper than the prediction. Okay, but talking about the solar cycle, let me show you all data concerning solar cycles in history. Well, since we are taking data, since we are observing continuously active regions in the sun, and that comes from the early 17th century. You might be aware of the observations made by Galileo Galilei, and we have data concerning the number of sunspots in our sun, and this is the variations in the last 4 centuries. So basically, this is what I was telling you about the solar cycle being periodic. because you roughly identify an 11-year period in all of these cycles. Obviously, you have peaks which are varying from time to time. So you are, for example, here looking at the very intense solar cycles like this one with this peak of about 200 active regions, and then you have lower ones and very, very tiny ones like this one at the beginning of the 19th century. And this is actually the last three. Well, this is already an old plot because actually this was before the solar cycle number 25 even started. So we have solar cycle number 24 and 23, which was very active, very intense. So let's see what happens in the next months and years, but apparently we are expecting to have the maximum of this solar cycle, of the current solar cycle, in about 5 years from now. That means 2026. Yeah, this is, well, it's obviously not very exact. I mean, you can have a variation in the order of months in the maximum of the cycle. Actually, most cycles are showing 2 peaks. As you notice here, there are 2 peaks. Well, one of them could be higher than the other one, but in this case, for example, in solar cycle number 23, you had 2 peaks which are quite about close to each other in the number of sunspots. Remember that if you have any questions, you can interrupt me anytime, please. You can open your mic or you can write down in the chat and I will be answering, if I can, your questions. So feel free to interact, and the idea of this session is also that I can get your feedback and see how is it going for you with the information and the things that I am presenting. Okay, finally, to talk about solar cycles, let me show you also this, which is what I was telling before. There are different predictions, so you can find in the literature different groups, research groups doing predictions, and these predictions are basically based on simulations on the one hand, but also on observations, previous observations on the other hand. So you have a lot of data from previous solar cycles, and somehow you can use that data to be able to figure out how the sun is going to behave from now onwards. Any question? I was hearing someone. Okay. Okay, yeah, I now heard something. So these predictions, as you might notice, are quite different one from the other. So some of them predict that the sun is going to behave less active than others. And this is very interesting because this is revealing, or somehow is showing, that we don't have the capabilities to predict well in advance how the sun is going to behave. And that's one of the, I won't call it mystery, but it's something that is reflecting that we still have to deep our knowledge about how the sun is doing.
We have a question, sorry, from Sigrid
Yes.
Lunga.
Okay.
Yes,
okay, yeah, the question is, what could be the reason of the 2 peaks? That's a tricky question because we don't have the answer. Actually, we have a model of how the sun is creating these active regions. Let me see if I have a video here to show you. Probably not. Okay. Yeah, I'm going to show again this video, which is showing how the magnetic field is placed in the inner part of the sun and is going like vertical in this image, in this animation. And then because of the differential rotation of the sun, remember that the sun rotates differently depending on the latitude. So the equator rotates faster than the regions high or low in latitude. And somehow this is disturbing the magnetic field lines, and they ended up crossing the solar surface. And this is what we call magnetic flux emergency. And this is creating active regions. So at this moment, this is what we can actually detect from our solar observations in the photosphere of the sun. And we can also detect the magnetic field. So last time I showed you what we call a magnetogram, and the magnetogram is basically telling you how the magnetic field is distributed over the solar surface. Okay, we're going to look at some magnetograms in a moment. So emergence of magnetic field is once again giving you a plethora of possibilities of how these different scales of magnetic field emerging, rise up in the solar atmosphere, and how they interact with the plasma already existing in the atmosphere of the sun. So this figure here is a sketch, a very complex one, but this is somehow showing how complex the activity of the sun, the interplay between plasma and magnetic field is going on. So this is the surface of the sun down here, this horizontal line, which I am pointing out. And then you have large loops, but also small ones, and a lot of words for what is going on there. For example, fibrils and canopies, and well, as you see, a lot of information. And basically what we are doing now in solar physics research is trying to complete the whole picture, because we have specialized in one region of the sun. For example, there are some groups interested in exploring the inner part of the sun by using, for example, helioseismology, which is this technique similar to the seismology that we apply on our planet, but in this case to be able to figure out how the sun is composed behind the surface of the sun, so in the inner part of the sun. But also there are some people interested in the action of this magnetic field and how the magnetic field interacts to each other, and how they produce this that we call reconnection phenomena. And from the reconnection you have release of energy. So let me show you some videos. These are videos from the Solar Dynamics Observatory, just for you to have a feeling of how we are able right now, by using a time series of images, by using single frames, we can complete, for example, the evolution of this explosive region. One more. Sorry, this is the same. Yeah, this one is a new one. Okay, so this is something that we can reproduce with our user interface, with our software, because it's just a matter of going to the date and try to look at the same region. Remember that we have the possibility to cover the whole sun. I mean, this Solar Dynamics Observatory is observing the sun as a whole. So we have the whole solar disk, and we can obviously go and just try to get a region of interest, and we can amplify the region. And that's very useful, I would say, because with other telescopes you are restricted to a very small region of the sun because of the obviously sometimes higher resolution. You have to focus in one single region, but you have only the possibility to explore that small region. In this case, we have less resolution probably than other telescopes, but we can go anywhere in the sun. And also, let me remind you that what we are looking at here, for example, are coronal loops. So these are magnetic field lines but obviously you cannot see directly the magnetic field, but we can see the plasma, which is confined inside these magnetic loops. So this is something that we can call an indirect detection of the magnetic field. And we have two main phenomena taking place in the solar atmosphere, energetic phenomena. On the one hand, we have flares, and on the other one, we have what we call coronal mass ejections. So many people are a bit confused on what the difference is between flares and coronal mass ejections. And the basic idea is the following. Flares are related to the release of energy. So you have radiation, photons being ejected from the sun, and that's radiation. On the other hand, you have coronal mass ejections, which are more related to plasma, to material, particles, but not light particles. I mean, not photons, but electrons, protons. So that's probably the main difference. What happens is that in most cases, you have both phenomena taking place at the same time. For example, in this one here, you have a flare, is releasing energy. Okay, but this is another one. This is a coronal mass ejection because you identify a lot of plasma being ejected away. But most of the time, you have the combination of the two. And that's why in most cases, we always analyze both, how the energy is being released, but also how the plasma, the material is being ejected. Okay, so before going again to the user interface, the graphical user interface, let me show you two very short videos of the Solar Dynamics Observatory and also another mission, which is called Stereo. So our plan for today's session is to explore another telescope, which is called Stereo. Well, actually, it's a mission with two telescopes. It's two twin spacecrafts. Unfortunately, one of them is already damaged. So we have only one available. But anyhow, I'm going first to this very short video just for you to have some information from this Solar Dynamics Observatory. You can find these videos in the NASA website. So you can type SDO, which is the name of the telescope. Once again, Solar Dynamics Observatory. Okay, so I put this one and we continue afterwards.
We need to understand the sun because the sun changes our lives every day. We all know that the sun makes the weather, but when we're flying things in space, astronauts, satellites, the sun affects them even more directly. The sun puts out what we call space weather. Space weather causes problems with our satellites, our astronauts, our communication systems here on Earth, and our navigation systems. We need to know more about how the sun works, where the magnetic field of the sun comes from, and how that magnetic field is converted into space weather. HMI is the helioseismic and magnetic imager. Very long words for something that's very useful to look at on the sun. The helioseismic refers to the sound waves that we can measure at the surface of the sun, that when we carefully analyze them, we can look inside the sun and see what's happening under the surface of the sun and even what's happening on the other side of the sun. It's much like how we use the waves from earthquakes to know where the earthquake happened, how big it was, to learn about what's inside the earth from earthquakes. At the same time, HMI will produce maps of the magnetic field of the sun. We're all familiar with the magnetic field of the earth. We use our compasses to point our way with that. On the sun, the magnetic field is much more complicated, and it comes up as little tiny pieces of magnetic field all over the sun. When they get together, they can be called active regions, very strong magnetic fields, but nonetheless there's a magnetic field all over the sun. For many years, people studied only the active regions. That was the thing that people really were worried about. We now understand that you have to worry about all of the magnetic field of the sun, and that's what SDO was designed to do.
Good. Okay, so this short video is telling again what I commented briefly before about the importance of the magnetic field. So basically, for our sun and for any star, the magnetic field is what I call the soul of the star. I mean, all the activity of the star is somehow related to magnetic field perturbations, magnetic field emergence, and the action of the magnetic field once it crosses the surface and enters the atmosphere of the star. I have a question here, which is from Chaima, and the question is, the dark spots are related to flares or to coronal mass ejections? And the answer is to both. So basically, in all places where you have these sunspots, these dark spots that we call sunspots, you have either flares or coronal mass ejections, but not always. I mean, not all the sunspots produce flares or coronal mass ejections. Only some of them, and that's something that we are trying to understand, how we can figure out when one of these sunspots is going to produce solar activity in terms of flares and coronal mass ejections, because not all of them do. For example, in this case, we have an active region of in the sun. Well, in this case, it's a little bit tricky to see the whole region because it's very close to the limb, to the solar limb. Let me enlarge a little bit here. So this is the border of the sun, and you can easily see this dark spot here. Obviously, we have a lot of projection effects. So if you have this sunspot, you cannot tell much about the actual shape of the sunspot. Only when you have it in the central meridian of the sun, you are looking at the whole feature without being projected. But anyhow, this is the surface of the sun in number 1. See, this is the photosphere, visible light, what we also call the continuum. And then we are going, like in atomography, we are going upwards or outwards, better, outwards. And these are the next layers. And you see how this dark region starts to produce brightenings. So somehow the dark region in the photosphere is producing bright regions higher up. So this is a typical flaring activity, and this is produced because of the magnetic field, which emerges and crosses the photosphere. Actually, I don't remember if I have told you why these areas are dark, and the reason is because of the magnetic field freezes the plasma. Well, freezes, this is an approximation because actually the temperature is still 2000 degrees in the dark regions. But if you go outside in the external part of the sunspot, you have probably 4000, 5000 degrees. But the problem is the contrast, because you have a very intense and bright area, and then you have a less intense area, but the change in temperature is about 2000 degrees. So the reason for this darkening is just because the temperature is being reduced by 2,000-3,000 degrees, but it still is very hot. So actually, if you will be able to extract an active region and put it behind, besides the moon, the full moon, for example, it will be much brighter than the full moon. And you all know that the full moon is very bright, but still this is much brighter. The problem is that you are contrasting it with something which is even more bright, even brighter, which is the surrounding photosphere. But then these brightenings here are revealing much higher temperatures. If you go to the last one, number 6, So number 7, well, number 7 is a combination of different bands, different bandwidths, but this one is probably up to 1 million degrees in temperature. But the way we characterize these flares is using a classification. So this is a type of flare from A to Z, going or passing by B, C, M, X, and this is the quantity that we are measuring here. It's watts per square meter. So somehow this is telling you how the energy is being released per volume and per time. And this classification is telling you obviously that the flares type A are not pretty much of interest, because even though they are ejecting material or energy also, is not as intense as, for example, Z, which is more interesting. So, well, in terms of space weather, I'm talking about, because obviously all this energy and material is going to permeate all the space around, and this is the main driver of space weather. And the problem, well, not problem, but the situation is that obviously our planet is not always, but in some cases, in the line of sight of these ejections. And I'm going to show an example in a few minutes. Okay, but let's go back to this website. First, let me read some questions here. Just a second. Okay, so Likita is asking, as you had mentioned, the sun undergoes differential rotation. So is there any project where we work on simulating the back part of the sun and try to study to an application or so? Or is this type of project feasible if it is not done before? Okay, so we can somehow follow active regions. Obviously, if you follow an active region from one day to the next one and the next one and the next week, well, you will have the possibility to measure the differential rotation. So actually, that's a sort of project that you can do, well, quite an easy one, because it only takes, I mean, you have only to take an image and measure the position of the sunspot, and then go to the next day and try to track the position of the sunspot every single day. So actually we can do it here. So this is from today's solar observation from this Solar Dynamics Observatory. So it's 12th of January. As I mentioned in the first session, you have all different filters here. You have up to 10 different filters. Each filter here has a number which is telling you the wavelength in angstroms. So you have 304, 1600, 1700. For example, these ones are a bit closer to the visible light, these two. Can anyone tell me what's the visible light? What's the coverage of the visible light in wavelengths in these units, angstroms? You remember that?
I know in nanometers, it's 400 to 700 nanometers.
Okay, so in angstroms, how much will it be?
Yeah.
So it's basically
1 meter is 10 to the power minus 10 angstroms, right?
that's
Or
it. Yeah, that's it.
Okay.
That's it. So the difference between nanometers and angstroms, basically, it's a factor of 10. So in angstroms, it will be from 4,000 to 7,000. So here we don't have any wavelength from the visible light spectrum, but these ones 1600, 1700. So this is close to 2,000, which is, well, not that close, but closer than the others, which are 304, etc. Okay. So for today's observation, we have, for example, magnetic field information. Remember that in the video, we were told that the helioseismic magnetic imager, that's the instrument which allows to track the magnetic field, to detect or to figure out how the magnetic field is. So HMI is this one, and we can go to the 4K, which is the full resolution. These images are 4096 times 4096 pixels. So this is the short version, the small version better, and this is the whole magnetogram. So once again, you have black and white, but this is only telling you, or this is only giving you the line of sight magnetic field. Line of sight. What does it mean? That means that you are looking at black, which are magnetic fields entering the plane of your screen, or plane of the sky, and white, which is the magnetic field going out from the plane of the sky. So this is only line of sight. But anyhow, this instrument will also allow you to get the full vector magnetic field. So what's the meaning of that? Obviously, the magnetic field is a vector, and you have you can have different directions, but this is only restricted to the directions along the line of sight, which are pretty much of interest. So this is a first approximation of how the sun is, how the behavior of the sun is in terms of the magnetic field. I forgot what I was going to tell. Okay, so here you have active regions which are more evident than the ones in visible light, because as I mentioned before, the active regions of the sun are regions where you normally find sunspots, but these sunspots are harboring intense magnetic fields. So the easiest way to detect these active regions is going directly to the magnetic field, which is what you're looking at here. And you clearly see that these regions are harboring black and white magnetic field. That means positive and negative magnetic fields. Okay. So if you go downwards here, you will get this ISOL search. I remind you, if you don't know, that sol is the word for sun in Spanish. So this is sun search. This is a tool that is detecting, it has an algorithm for feature tracking, or well, actually feature detection. So you have the possibility to tick in all different options here, and you get the location of these features. I'm just trying to see if I can enlarge this thing. Probably not. Okay. Like this. Okay, so if we untick all of them, you will see the blank sun. Hopefully. Wait. Okay, yeah. So if you want to locate the active regions, you can just tick in active region, and then you put search, click on search here, and hopefully I don't know if I press down many times and I spoil it. Clear again. Okay. If you are doing the same and you have success, just let me know. I'm going to do it again, because probably I press it many times. Okay. So once again, in this case, this is telling you where the location of active regions is, coronal mass ejections, coronal holes. I will talk about coronal holes later on. Don't worry about that. But anyhow, the intention is that you recognize that there are a lot of different structures and they can be detected and they can be tracked. If you enlarge, for example, this region, you see some of them. Well, these are sigmoids. This is the shape of a magnetic field that looks or resembles an S, and that's called a sigmoid. But the point about this interface is that you can also go to, for example, publications in the literature about that region in particular, or you can go to HelioViewer, which is the software, but the online tool, and you can get the data also. So if I press here, get SDO data, this is something that puts you straight away into the website where you can actually ask for the data. So you can order the data. And this is because obviously in this training session, I'm telling you, or I'm presenting the way to explore solar images. But obviously, if you want to analyze in more detail those images, you probably would like to get the original files, the feeds files, and try to apply your own algorithms or whatever you are doing. And this is obviously something useful if you are doing a research project and you want the raw data or the different levels of data. So I encourage you, if you are interested in this one, to, for example, order some data and try to see what you get. Okay, and some others, like, for example, coronal mass ejections. Let me check if we have any coronal mass ejection here. Probably not. Okay. Yeah, at the moment, I don't know if this tool is actually, if it updates every time I click, or if I have to search here. That's something I don't know. Because actually I normally don't use this tool, but the other one, which is the JHelioViewer. So I'm just showing you this because this is the base of the JHelioViewer tool, which is the one that probably condenses all what I'm showing you here. Okay. So let me go. If you don't have any more questions, I'm going to check the chat because we are going now straight to the JHelioViewer once again. So be ready to open the JHelioViewer. For the ones who are probably new, HelioViewer or JHelioViewer is a software that you can download into your computer, any system, and you just click here, download HelioViewer and JHelioViewer, and you have the interface, which I'm going to open right now in my laptop. And let's see what we get when we open the interface. We should be able to have a look at the more recent data from SDO. So you have the date here. This is 10th. Oh, well, actually you have the last 2 days, as you see from here. So this is 10th at 12:50 UT. Remember that the time is always in UT, Universal Time. So you have from the 10th to the 12th. So you have 2 days, 2 whole days, but you need data. I mean, this is only the initial and final time, but you need to get the data from a telescope. So basically, You have the SDO here, which is the one I'm talking about a bit more than the others, because you have a lot of data to select. You have 10 different bandwidths. So what if we go for AIA, which is the instrument atmospheric imaging assembly, and 171 angstroms. So let me press there. And the software is going to the repository where it gets the data from the Solar Dynamics Observatory in 171 channel. Okay, the color, remember that is only a tool, because obviously 171 angstroms is out from the visible range, but this is a color that you can put. So the SDO has a color palette for all different data. Actually, if you want to change the color, well, you have different possibilities. Down here in the color option here, you have many possibilities. For example, if you want to use the color that normally SDO uses for 193, you can do it. Or you can go to another colors from this color palette. Obviously, this can be a bit confusing, because obviously you are presenting 171 data, but down here it says 195. But this is only because you are using the color palette that channel 195 uses. So I don't recommend you change the original one, unless, for example, you want to go to another options. Well, actually, you have different color palettes also for another telescopes like SOHO. This is another very famous solar telescope, actually a bit older. It was launched in 1995, but it's still working pretty well. Actually, these images, from the coronagraphs that we presented last time, LASCO images, those are taken with this telescope, the SOHO telescope. But also you have a stereo. But anyhow, I don't recommend you play too much with this. Well, you have also options in different colors, like, for example, blue, green, red, yellow, or blue, red, whatever. But I prefer to stay in the original one. Okay, any question, any comment? Please, I hope you all are now at the same place in this JHealy viewer tool, so that we can follow what I'm doing. Okay, remember that you have the possibility to use your trackpad or your mouse if you want to zoom in or out. You can move around. Well, actually, from now, we can close down these timelines. Just for the moment, I will comment on that in a moment. Let me check the chat. I have a question here from Rogers. Yeah, Rogers is talking about one important aspect about the activity of the sun, and it's related with the space weather, but how space weather affects our own planet. And yeah, basically, when you have this solar activity expressed in flares and coronal mass ejections, you have a higher chance of this plasma and this energy to impact our own planet. And that's when you will probably have problems with the communication devices, technology developed by humans, satellites. Obviously, we have we have thousands of satellites in the space, and they have been launched in the last 60 years. And from day to day, we have more and more of these satellites, which are obviously affected more than we are on the surface of the Earth, because they don't have the protection of the magnetic field as we have. Well, not as much. And also the atmosphere protects our planet from, for example, UV radiation in particular. So that's something related with the importance of understanding space weather and related to the importance of being able to forecast the solar activity. So that's why with all these bunch of telescopes, we are somehow being able to track the evolution of the sun. And this obviously has to be completed with simulations. We are using a lot of machine learning for trying to predict what's going on in our star. Okay, so I continue here. If we use these options here, you can, for example, move around, you can rotate, and you can see what's behind. And obviously, you get nothing from behind because you don't have any telescope observing the sun from the back. And also I commented last time this, which is something related with the projection effects. So obviously, if you are looking at the sun like this, you have all the information from the center of the sun, from the central meridian, very clearly visible. But if you go to the limb, you start to have these projection effects because of the sun being almost perfectly spherical. So if you look around here, you will see these projection effects. And also, if you look it from below. Well, I'm telling above and below, but remember that we don't have a direction in a space. This is only respect to our own point of view. But this will be the solar South Pole and the solar North Pole here. And you also have this option to use a different projection. So this one in particular is called an orthographic projection, but you can use a different one: polar, log polar, latitudinal. Let's click on this one, for example, latitudinal. Probably you are more used to these images with the images of our own planet. I have a question from Heather, and he or she, I don't know, sorry, is asking why, we don't need to observe the sun from the back, right? Well, that's what we want, to be able to observe the whole sun all the time. But that means that you need a lot of coverage. So you will need telescopes from this point of view, from our own point of view, but also telescopes at the back, so that you can complete the 360 degrees of solar observation. But let me tell you that we have done that. Not always, but there are some examples of the whole sun being observed at the same time from behind and from the front. And actually, I want you to reproduce that observation and being able to see something like this, but with the whole sun, the whole coverage around the sun. So that's something that we are going to do in a few minutes. Okay, once again, this is latitudinal. So this is showing the information differently, obviously, on a plane. And let me also remind you that you have different options here. For example, you can artificially increase the sharpness. Actually, this, 1 second, because this should be work. Let me refresh here. Yeah, I have to tell that also sometimes you have the program running a little bit slow. So don't get desperate, especially when you are using a lot of images. For example, here you are uploading, well, 97 images, and these images are quite big. So this is more than full resolution, full HD. So that's something that probably will get many of the resources from your computers. Okay, sharpen. Well, actually, this is somehow not doing anything now, but anyhow, this is only for getting artificially a better sharpness value. But the levels is something that you might want to change. And this is changing the displaying intensity levels. For example, if you want to focus in one of these regions and you want to see, you want to detail things, you might want to vary these levels. Okay. Okay. Also, remember that you have the option to present what we call the running difference. Running difference. What does it mean? Well, first of all, let me put it again to reset camera here to go back to the original display option. And if we go to running difference here, because at the moment you have known difference, if you press running difference, that means that you are subtracting two images. So in this case, because moment, please. Just want to check if we, yes. I just wanted to check that we have the whole time series. I mean, if you press stop and play here, because obviously all these options can be activated while the movie is running. So if you press running difference, what you're looking at here is a very interesting tool because you are subtracting images. So this is presenting one frame minus the previous one. Remember that when you have an image, you have a matrix, basically. So in this case, this is subtracting matrices, one from the one before. And why this is interesting? Because this is telling you very much about how the information is changing from time to time, from image to image. And obviously, this is something that can highlight even more the activity of the sun. So if you have white, that means that the subtraction is positive. If you have white here, if you have a black value, this is telling you that the subtraction is negative. But you can almost identify very nicely the loops, the coronal loops, which are representing, well, are tracing the magnetic field of the sun. Okay, so in terms of the, let me go back to this one, in terms of the levels, because Nimi is asking me probably of this, what happens when you change levels, what you are doing. So basically you have the possibility to change the intensity range of the image. Obviously, this is not affecting the original data. That means that this data is in a repository somewhere. I don't know where, but probably this is from the Royal Observatory of Belgium, where you have a repository. But anyhow, the original data is always the same. But these tools are only for visualization purposes. That means that here you are changing the intensity, the minimum intensity level that is going to be shown here, and the maximum one. Okay. Well, what else we can do here? Well, you have the option to change the grid, for example. Here on the left, you can have the grid, which obviously is important because somehow is, well, it gives you the possibility to measure values, to quantify, for example, the distance from the center to one of these regions. Actually, this is the value of latitude. So this line, horizontal line here, is representing 20 degrees of latitude, 40, 60, 80. And so in the solar latitude. Okay. So once again, running, and there is also one option which is called base. What's the difference between the two? Because if you look at base, it looks more intense. I'm going to reset my camera. So base here and running, I'm going to blink between the two. So running, base, running, base. The first thing that you notice probably is that in the running, changes appear to be more rapid, faster than in base. The difference is that both of them are subtracting images. Running is subtracting one image from the previous one. Yeah, the difference between two consecutive images, and base is subtracting the original one, the first one, sorry, not the original, the first one. Always any frame minus the first frame of the series, of the time series. That means the frame at 12:50, the 10th of January, the first one. So I recommend to use better running because this is displaying, or this is giving you information of instantaneous changes. Base is giving differences between one frame and the initial one, the first one. So this is more tricky probably to understand or to get a physical meaning of this one, but from running it's easy because this is telling you how the sun is changing from one frame to the next one. Okay. Well, so we are going to look at, again, let me stop here and let me go back to the solar monitor because I want to show you a bit more from this space weather. So if you go to the space weather website, at the beginning, you have this information, another far-side explosion. A huge plume of hot plasma just shot up from behind the sun's northeastern limb. It's the latest explosion from a far-side active region, which will turn to face Earth later this week. Amateur astronomers with solar telescopes are encouraged to monitor developments. Let's click on this one. Huge plume of hot plasma. What does it mean? This happened a few hours ago. How many hours ago? Let me check the time now. This happens 8 hours ago. And this is what we call a hot plume. Basically, it's a coronal mass ejection. So it's material being ejected from the sun, and the time is 4:29 UT. So what if we go to our J-Helio viewer and try to upload this data? Okay, so that means that we have to go to J-Helio viewer and we change the times here. So we can put initial time, we go for today's observation, 12th of January, and let's go to the time 3:30, just to cover a bit earlier than the actual time of this ejection. And then below we have the 12th of January, and let's put 5:05:30. So we are looking at 2 hours of solar observations from this morning. Well, this morning in UT time. After that, we'll press enter and then synchronize. Yeah, sometimes you have problems, as I mentioned before, with the, well, either the internet connection or your RAM memory, and you could have, for example, some blurring images, but don't get desperate. Just, you have to be a little bit patient and probably just close down different applications that you are running at the same time in your laptop so that you can have the whole space in memory for this. Okay, so I think all images are already uploaded, but then we have to press play. And that's it. Okay. Okay, so we are looking at the latest eruption from the sun. So this is latest information, and let's explore it in more detail. We can use these options up here: track, corona. Well, corona is something that only extracts the solar disk without any information from the corona. So in this case, we don't want to press corona because otherwise we are not able to look all what the information coming from here, from the limb. And track, you can press track and move around. Move. Wait. Okay, so track is if you want to concentrate in one region, and the sun will, the software, sorry, will keep that region still. But that is something that we cannot test here because we have only 2 hours. So in 2 hours, you don't have a lot of rotation of the sun. But if, say, you are looking at 2 weeks of solar observation, then you have a lot of rotations. Well, probably one rotation, but things are moving from east to west. In that case, sorry, from west to east. In that case, if you want to track a region and put it still in front of you, then you press track. Okay, but I don't want you to get confused by now. So let me go into more details about this region here. What, for example, if we upload more data? Any question? Any?
I saw a workshop too.
Okay, yes, someone. Let me check. Okay. Okay, I continue. So
it's about the screen. Your screen is very blur. So
okay. Okay, yeah. Yeah, if the screen is blur, it's just because of your laptop. Either you are having problems with the RAM memory or internet connection, obviously, because these images are being are taken from the repository. So you need a good internet connection. The more images you upload, the better connection you need for running the whole thing smoothly. So if you have this blur, try to either close down, for example, any websites that you are using that are uploading information, or okay, you see blur my screen. Sorry, I was okay. So the problem probably is mine. So let me check one moment if I can. Yeah, okay. Sorry about that. I misunderstood. So the situation is that you are looking at my screen a little bit blurred, and that's something related with what I was telling, but for me. So just a second. So in the meantime, I encourage you to change a few things here and try to see how this affects the display. Actually, I'm going to stop sharing just a moment and try to share again. Yeah, but probably this is something expected because obviously, okay, yeah, it's okay now because actually I'm controlling the situation from another laptop. Okay, so now you should be able to look my screen a little bit better. Okay, I was telling you that what if we upload more data? Then stop here for a moment and try to go to new layer, and we are going to put another one. So which one? Let me think about it. Okay, let's put 193. 193. That's a one. Came up, and we have the bar complete here. Then we can press play. So in this situation, we are combining information from both channels. So you can either press only 193, and the other one, 171. Remember that 171 is in running difference at the moment. So if we go to normal, and we also go back to normal here, because remember that we changed the levels. Okay, so this is more or less the original information from 171 and 193. Okay, so I'm changing here on the left the two images, between the two images. Okay, let's see the situation in 193. So if we focus on this region, we can use pan here, this pan, to move around. So we can, for example, focus on that region, zoom in. Okay, so I stopped there because basically this is the time 443, right? When you have the eruption. Okay, and finally, let's put another channel, the last one for this example. We can put the channel 211. So basically we have channel 171, 193, and 211. 211. Okay, this is channel 211. This is the original color palette that they use for channel 211. Again, we have the eruption here. So remember that all these observations in different channels are simultaneous. Well, almost simultaneous. In some cases, you have differences of just a few seconds, but in principle, they can be all taken as simultaneous. Great. So now let's do the following. Sometimes you want to detail a little bit more the eruption and how the eruption affects, for example, other parts of the sun. So in that case, the recommendation is the following. You can play around with the channels and do the following. For example, I will start with the 171. 171, then you go to running, because as I commented before, running will allow you to detail much more the changes, small, rapid changes due to the eruption. So let's put it in running, and then let's use a color palette, which is different. You can, for example, use a single color. So in this case, for the channel 171, I'm going to use only the blue channel. Let's play the movie. And also levels can be changed to cover the whole range, the whole intensity range. So you don't want to miss any information from the intensity. You want to display the whole range of intensity. Okay. And also blend, this is for combining information. That means that if you have, for example, two different channels, blend is combining information 50-50 in this case. So 50% of the channel, and then if you put the other channel behind, you will have 50% of the other channel. But in this case, let's go to 0 from the blend. So we want, again, the whole image, the whole information. Eruption is not visible on the screen. Oh, wait. In your screen, right? Yeah, Nimi. That might be because you are not in the correct time. So check that you are covering the time of the eruption, which is 12th of January, 4:30 UT, 4:30 more or less, 4:14. That's one of the things. The other one is that maybe you are using, for example, a different level. And in that case, if you change too much the levels, you can end up disappearing or making the eruption disappear because of intensity only. Not that the eruption actually disappears, but because of you are only displaying some intensity levels, then probably the eruption is out from those levels. So just check all these parameters: opacity 100%, blend 0%. That means that you are not going to combine information. A slit, let me show you that a slit is just something that covers the image. You can cover the whole image, or you can open the whole image. I never use this one, but well. Sharpen is some artificial tool that sharpens a little bit the image, but also you can leave it in 0. I mean, we don't want artificial things. Okay, so this is channel 171. I hope you are following me, because now we are going to untick 171 and we are going to display 193. 193. By the way, in this channel, you can easily identify what we call coronal holes. I don't know if you are aware of this word, coronal hole. It's funny because in some places, well, in the media, you sometimes hear that there is a black hole in the sun. I don't know if you have ever heard about this, a black hole in the sun. No, it's not a black hole, it's just a black region in some channels like 193 angstroms. And this is telling that the magnetic field here is a little bit weaker in the corona of the sun. So this is what we call a coronal hole. So in some sense, it's a hole in terms of the magnetic field being less intense in that region. That has some implications, for example, that the particles which are going outwards from below can be ejected more rapidly, because they don't have the magnetic field which somehow stops them. But anyhow, this is something that you can observe from this channel. So in channel 193, again, we're going to put running difference here, running difference. We want the blend to be 0%. We want the levels to cover the whole intensity range. And we are going to use another color. We are going to use the color green down here. So only the green. Okay. Okay. And finally, I'm going to present channel 211. This normally has the palette in purple. Again, you have the coronal hole here, very nicely traced. But now I'm going to put running difference. We are going to down blend to 0, levels to cover the whole intensity range. And the color we are going to use is red. Red, okay. So in summary, we have 3 channels. We are using running difference for the 3 channels. We are using 3 different colors, red, green, blue. This is the palette with the fundamental colors. So it's that something that we can call the fundamental color palette, red, green, blue. And now we can, well, again, blue, green, red, but now we want to tick all at the same time. And this is what we get. So this is combining information from 3 different channels. Every channel, I remind you, that covers different temperature ranges as well. And we are tracing the eruption. So now we can interact with the display and try to look at the eruption in more detail. Yeah, probably because I am sharing my screen, you don't see the same level of detail that I'm looking at now in my own screen. But if you do this by your own, probably you will see a better definition of things. Actually, it has a stop. Yeah, and I'm sure this is because of memory issues. Yeah, yeah, if I zoom in, I have problems. Okay, it's running, but not as it should be doing. Yeah, but I'm sure you, with these instructions, you will have the possibility to explore an example by your own and try to see more details. But again, every time you upload more channels, well, you will have more problems with your RAM memory. So that's why, for analyzing images in general and solar images in particular of this level of resolution, you need very good capabilities of your computing systems. Okay, let me rotate here. So again, we are covering only half the sun and so on. And actually, this eruption is not very spectacular. So I put it here just for you to see the latest information from the sun. So this is something that you can actually do almost in real time, only a few hours after it actually happened in the sun. Okay, so I will stop here just because I want to comment on some more options down here. So if you go to timeline layers, this is this is another one. So we have 2 timeline layers here, or you have a space weather event knowledge base. These are 2 other options that I'm going to present right now. So let me reset the camera up here just to put the original display. Okay. Now, timeline layers. What is this? This will open something that will appear down here, timelines. You notice the arrow here. You can open or close this, and this is going to present a plot of the evolution of the information. That means we're going to plot what we call a light curve of the whole sun. But for doing that, you need to upload a new layer here, new layer. So let's press here, new layer, and you have different options. But the default one is this GOES XRS. The thing is that GOES is a telescope basically that is looking at the sun in X-rays. X-rays, you know, that is a very intense electromagnetic radiation, much more intense than visible light and even than UV light or UV electromagnetic radiation. So if you add the information from GOES, what you get is the variation of intensity. Well, it's related to the energy, but actually it's watts per square meter in logarithmic scale. So this is taking the whole zone as a source of energy in X-rays, and this is telling you how the X-ray information is changing from time to time. And you can play around with these plots. You can actually also increase the range in X, for example. Let me check. Yeah, I can increase the whole thing so that we can focus on some region. And what you're going to notice is that when the eruption is taking place, you will see an increment here in the energy in X-rays. So you can do that in real time by playing, and you see. Also, you have the option to stop the video, the movie, and you can move around this vertical line so that you can place exactly at the moment when the eruption starts. So because this is taking the whole sun as the source of energy, anything that appears on the sun, it doesn't matter when, it doesn't matter where in the sun the eruption is taking place, but this is taking the whole field of view and is computing or calculating the intensity in watts per square meter for the whole field of view. So this is what we normally call a light curve. Oops, I don't know what I did. Okay, yeah. So let me play a little bit just for you to see the whole thing. I just want to confirm if you are looking at the eruption in your own JHelioViewer tool. You can just put yes or not in the chat. Okay, good. Thanks, Sarah. Well, this is very useful because sometimes you have multiple eruptions. So this is actually a very tiny peak. If you have a X-flare, you will see how this goes up to almost going out from the plot. Okay. Well, you can still play a little bit more with all these options like base. What I like from these images sometimes is that they look more like artistic images. Actually, I'm very much interested in art and science, and once I did an exhibition using solar images in a gallery, an art gallery, and there were many people quite astonished by these images. Okay, now we are going to use another option from the left here, and that's the one. Let me put it in running again. The viewpoint one here. Viewpoint, you can click on viewpoint. Actually, if you click, you activate the option, but also you can click in the name, and then you have more options coming up. So viewpoint is the way you look at the images. And at the moment, we are looking at the images from the point of view of the observer. Who is the observer in this case? Well, the spacecraft, SDO, because that's the one we are using. But we can also put the observer on the plane, the ecliptic plane. Well, actually, sorry. Yeah, I forgot. This is a new option. Actually, the new version that was released a couple of weeks ago has many new tools. So this one is the Viewpoint Heliosphere, and you can choose the observer to be placed either in Mercury or Venus or our own planet, which is the one we are using now, the Parker Solar Probe, the Solar Orbiter, and many other spacecrafts, and actually planets as well, Jupiter, Saturn, etc. So what if you go to, where do you want to go? Let's go to Mercury. Let's go to Mercury and see if this works. Well, the problem is that now I might have to stop here and only, well, actually, I'm going to close down some of this data just because what I'm going to show you now doesn't need to have different channels because it's only view options. So let's go back to known. I'm just going to go back to the original situation, normal situation, let's say. Reset camera. Okay, something like this. Oops. Okay, that's the normal situation. Once again. Okay. Well, actually, this is good because also you can have a look at how the eruption looks like in the 171 channel, etc. So once again, viewpoint, you can click there. You can go to viewpoint and let's go to a different planet, Mercury. So this is how the sun looks like from Mercury. Obviously, you don't have the whole information from the sun because you are limited by the observation which is being done from the Solar Dynamics Observatory, which is more closer to the Earth's viewpoint. So Mercury, Venus, but we can also go farther away, for example, to Jupiter. Let's see if this works. Is loaded. Okay. Actually, I have to confess that this option was quite new for me. So I don't know the details, but it should be changing somehow. It's not. Okay. Okay, let me play a little bit just to make sure that this is doing something. Okay, yeah. Okay. So again, observer is the normal situation. If you go to location, you can change the viewpoint. You can go to Mercury. Obviously, you will see the sun much closer and from the side. Venus, you will see the sun a little bit closer than from Earth. Then you have Earth, and then you have the Parker Solar Probe, which is this mission, which is going around the sun quite close to the sun. As you notice, this spacecraft is actually behind the sun because from there you can only see a tiny fraction here of the sun. That means that you are behind the sun. Solar Orbiter is another mission. This one is almost looking at the whole sun as we are looking at it from Earth. And we can go to other missions, Bepi Colombo, a mission to Mercury. These two ones, I'm going to comment those ones at the very end, which is in about 20 minutes. I don't have much time, but anyhow, we are going to talk about Stereo. But Stereo is a mission launched in 2006, two spacecrafts around the same orbit as Earth, but one going to the left and the other one to the right. And basically the idea was to look at the sun from two different viewpoints, sorry. So Stereo ahead and Stereo behind. So once again, okay, look, Stereo ahead. So you're looking at the sun from ahead and from behind. SOHO, that's almost the same viewpoint as from Earth. And SDO, Solar Dynamics, this is the one we are actually looking at now. But you can also look at the sun from the moon, from Mars, Jupiter, and you will start to see how the sun shrinks down because you are farther away. And Uranus, and Neptune, and Pluto, finally. Okay. This is a nice tool, but basically it's not giving much information because obviously you are using only the data from the spacecraft, which in this case is SDO. But anyhow, it will show you how the planets are orbiting Earth and how the viewpoints from different planets obviously change because of their own orbits. Okay, now I would like to concentrate in this Stereo mission. So I'm going to stop my screen just for a moment because I'm going to put a video. I just want to confirm I have this sound activated. So basically, I would like you to watch this very short video also. Well, 4 minutes, but this is very interesting because it's telling what the idea behind the Stereo mission is. So please enjoy the video.
Stereo is a mission to help us understand what we call space weather, how the activity on the sun can affect us here at Earth. The sun will blow out what we call coronal mass ejections. They're a kind of solar storm, 1 billion tons of matter coming at us at 1 million miles an hour. And they can affect our technology here on Earth, affect power systems, affect spacecraft. And so understanding them is not just a case of their scientific interest, but it also has practical application. These two spacecraft are giving us two views on the sun instead of just one. And that's really important because the structures that we're looking at the sun, that are in the solar wind, which is the sun's atmosphere blowing out into space, really three-dimensional objects. And to really understand what we're seeing, we have to look at them from more than one point of view. CMEs, looking at them, they're kind of like big puffs of smoke. They have structure, but you can look right through them. In general, you can sort of think of CMEs as a kind of big bent slinky. And by looking at it from more than one point of view at the same time, we were able to confirm that that's roughly what CMEs look like. The sun's super hot atmosphere is flowing out into space constantly, and this is called the solar wind. And coronal mass ejections are kind of like storms in the solar wind. You can see from a distance the large scale of these storms blowing out into the solar system, but we can actually sense in a number of locations throughout the solar system, Stereo and other ones, the actual disturbance as it goes by. So we can sample the solar wind, see what that's like, sample the CME as it goes by, and putting all those together, the remote sensing data, the local conditions, have given us a really good, complex picture of coronal mass ejections that you can't really get from a single spacecraft. Comet tails respond to the solar wind, and we've known that for a long time. They're basically charged gas, and they're interacting with the magnetic field in the solar wind. But what we see here is all the dynamism in this tail. And you can see that it's not just sort of a straight tail, but that it's responding. You see there, right there. It's responding to this coronal mass ejection that's coming out from the sun. So it helps us understand how the comet interacts with the solar wind. We can actually use the comet sort of as a way to probe the solar wind. So stereo allowed us to see the far side of the sun for the first time. You look at the sun and you see these bright regions, these active regions. That's where things like solar flares occur, and really big coronal mass ejections will often come from near those. You might not see anything on the side of the sun facing you, but something really interesting might be developing on the far side of the sun. It can be a surprise when it comes around. You know, we might have some inklings that something's going on back there, but we can't really see it without, for instance, stereo. So this was a major solar storm. We would have known something had happened, but we wouldn't have understood its magnitude just from data on this, from the point of view of the Earth. And if you look in the coronagraph image to the right, you'll see that suddenly there are all these little bright, like bits of snow that show up on the detector. Well, those are called solar energetic particles. And what they are particles that are accelerated almost to the speed of light. And those can be quite hazardous to, for instance, spacecraft or astronauts. They are related to these coronal mass ejections and other kinds of solar activity called flares. And we would never have even known that it was happening without spacecraft on the far side of the sun. So by putting all these different points of view onto the sun and space weather, we've been able to understand our star in a way we've never been able to understand before.
Okay, so I hope you have enjoyed this video, which is very, well, interesting because it clearly gives you the idea behind observing the sun from an interesting viewpoint, which is getting information well in advance compared to the one we can obtain from our point of view from Earth. So if we go to, for example, today's observation from a stereo, then we can go here and change the channel, well, the telescope and the instrument and everything. So basically, stereo A is here, and you have different possibilities. You have full these observations in 171, 195, 285, 304. So again, you have different channels. In this case, only 4 channels compared to the 10th channels that you have with the Solar Dynamics Observatory. But anyhow, let's use, for example, 171. And this is something that can happen, and is that the information is not uploaded yet. So basically, this is not having the information from today's stereo observation, because obviously it takes more time, and probably a couple of days for the information to be available in the repositories. But as far as I remember, you have this information from the coronagraphs. Let me check, for example, this one. Okay, no, you don't. So we have to, in that case, move to a previous day. So let's go, for example, to the 1st of January this year, and try again. 171. Data is available on or after. Okay, so we have to go back to the previous year. Oh, sorry. I didn't change the time. So that's why, yeah, I was keeping the same time. So we have to go to 1st of January up here, and also, well, let's try to put the same 1st of January, a couple of hours, and 171. Again, error encountered during no images were found. Okay, so let me do the following. Close down everything so we don't have any channel at the moment. And I'm going to reset the camera. Also the viewpoint. Remember that the viewpoint at the moment is in Uranus, so we're going to observer view here. Okay, so we are again in the initial situation. So once again, let's try to change here 1st of January, 1st of January, and 1st of January. So we have initial time 1st of January 3:30 and final time 1st of January 5:30. So only 2 hours here. And now let's put new layer here, stereo A, and try again. 171 Secchi is the name of the instrument, and this means extreme ultraviolet. 171, and no images. So I'm afraid we have to go back in time. So what if you go to the 1st of January 2021, so a year ago? Instead of this year, let's go back 1 year. Okay, and try again. I don't know if I have to press synchronize first. No, probably don't, because we don't have any data to synchronize. No, it's not giving information. Okay, let me go back in time to one interesting observation from stereo on the 26th of March 2007. I will let you know why I want to go there. And that's the last chance we have to get the data. So 2007, March the 26th. Here, March 26th. Okay. And final time, again, 2007, March and 26. Possibly we can change the times here. We can go from 00 to 00:30 to 10:30. Okay. Okay, press enter. And now try to do the same. Stereo A, 171. Okay, it's working now. Rogers is telling that he's having problems. So if you want, because apparently you are not seeing my screen, can't see anything behind being shared. Well, what you can do probably, Rogers, is you can go out from the session, from the Zoom session, and try to get in back again, because it's probably something related to your Zoom application. Okay, look, we have the stereo information for 2007, again, March the 26th. What I'm going to do here is to look around. Obviously, you have half of the sun without information, because this is the viewpoint from stereo A. Where is stereo A? Or actually, where was in 2007? What we can do is change the viewpoint and try to see the location, change the location. So at the moment, if you are located on Earth, wait a moment. Observer location. Okay, it's almost, look, observer is the telescope, stereo. So it's almost the same as the one from Earth, only a little bit different, but basically the same. But what I want to do is to upload information from the other spacecraft, stereo B. So we're going to upload a new channel, a new layer with a stereo B in channel 171. So we are using the two satellites, and we are combining the information from both satellites on March the 26th, 2007. And the reason is because at that time, both satellites were in a situation that they were covering the whole sun. That means that if we go to stereo B, look, stereo B is covering the sun, but if we put stereo A at the same time, oh no, wait. Something related with the viewpoint. Yes, sorry, the viewpoint. No. So probably I misunderstood something because I was checking the website. What I did was the following, because the two satellites are orbiting Earth, but one is going to the right, let's say, and the other to the left. They are covering different viewpoints. One day they were looking at the sun from the two sides. That means that one of them was looking at half of the sun and the other one was looking at the other half of the sun. If you combine the information from both, you should be able to cover the 360 degrees. So let me recheck again the date. Actually, I can do it with you. Look, I can put it here. Full sun seen from stereo emission. Okay. So it says first ever stereo images of the entire sun. That's what I want to reproduce. So let's check again. This is what I want to see. Okay, yeah. So I had the wrong date. So I extracted that one from a website, but probably it's not a good one. So February, that's the right one. February the 6th, 2011. February 6, 2011. Okay, so now we can go back to our tool and we change the time. So we're going to 2011, February the 6th. Okay, and final time, again, 2011, February the 6th. And we can keep the times, well, actually, this one, let me put it again, February the 6th. Okay, now, so once again, 2011, February the 6th, 2011, February the 6th, but the time is the same. We have to change this one because otherwise we don't have a coverage. So 00 from, let's say, 05. Press enter here and synchronize. If you don't press synchronize, you don't have the information going into the channels or being updated for the channels. So now we have the information finally. So once again, I'm going to reset everything because I want to show you stereo A. Stereo A is here. If I press stereo B, I don't have any information. Why? Because you have to move around. Spacecraft was behind. So now if I press stereo A, I have the whole coverage. Half of the sun is covered by stereo A and the other half is covered by stereo B. And that happened on February the 6th, 2011. That was the first time in history that we were able to look at the sun, the whole sun at the same time by using these twin spacecrafts. The problem, unfortunately, is that in 2014, stereo B was damaged. So since then, we only have the possibility to look at the sun from stereo A, stereo ahead. Okay, but what if we, any question? Sorry, I didn't ask before. Any question? Have you been able to reproduce this observation, which is pretty nice? Obviously, you have these projection effects near the limb. But anyhow, it's a very interesting observation. And you can actually play the movie. Let's see. Well, not the best one. See, yeah, the thing is that we don't have too much images here, only 19, but we can change the final day to the next one and try to see if we can gather more images just to be able to identify evolution. Okay, I'm gonna finish in 5 minutes because I don't want to take much more time. Okay, now it's working. Well, it has some problems. Okay. Yeah. It is working. Good. So in the Slack channel, I will put you some, well, a few exercises, probably a couple of exercises for you to just have a look at the data on the date we are interested in, and you try to gather as much data as you can to be able to trace or to track better, to track, for example, the evolution of a region in the sun. Also, you can get information from the coronagraphs on a stereo. So this, well, sometimes you get to not being able to find the data. That's something that can happen. So I'm going to reset the camera again, stereo A. I'm trying to upload the image from the coronagraph in a stereo B. Oh, stereo B, then I will put better stereo B in front here. And let's see if we can have the coronagraph information. I don't see it is working. Yeah, we have stereo B, stereo A, but somehow we don't have information from the coronagraph. Okay, so very final example, very quick, because I just want to very rapidly upload data from SDO again. And this is gonna take me only a couple of minutes. Okay, I just want to show you how we can upload the coronagraph data, but not from stereo, but from SOHO, which is probably better known. I did an example last session. So we can upload information from LASCO C2, that's a coronagraph, which is looking at the sun from 1.7 to 6 solar radii. Ah, crazy. Yeah, the information wasn't appearing before because I had activated this corona. And if you do so, you are limited to the inner part of the sun, the solar disk. So be careful with that. And actually, that's something good that happened to me now because you will be more aware. So the corona will change the situation of what it's around the sun. So please be careful with that. So now we have the corona information from LASCO C2, and I'm going to upload LASCO C3 finally to have the whole coverage. So remember, LASCO C2 coronagraph 1.7 solar radii to 6 solar radii, and this one LASCO C3 coronagraph up to 30 solar radii. And what I wanted to show you here is the option to change the grid and to put a radial grid. So you have the option to solar axis, to put the axis in the solar disk, this one, solar axis, this one. You have the option to put the grid. But if you want to use the coronagraph, you better use radial grid. Okay. And then you can play the movie. And see the evolution. This is taking some resources, obviously. But this is good for you to have a reference of how the solar wind is moving respect to these radial coordinates. And also, I encourage you to follow a coronal mass ejection. You can have a look over the internet, a strong coronal mass ejection, and you can just write down the date and you can look at for the data and try to follow the evolution of that CME. We did something in the first session, and there were some exercises also for you to do. And remember to play around with all different options. There are a few more that I didn't have time to cover, but basically another one which is of interest probably for some of you is to, is to go to this SDO cutout, and this will point you or address you to the website again, where you can download the information. So try to do that, please, to order information, and you will get the feeds files for this. And the movie, you have an option to make a movie. Which I don't find right now. Reset camera. You have the option also to share information. You have the option to the multi-view, where you have all information in a separate display. So I hope you have enjoyed the training session. Obviously, we have a limited time, but as always, this is something that you learn. The more you practice, the more you learn, and that's what masters do. So please, if you have any question, let me know. We can still use the Slack for exchanging information, and I'm very happy to give you further information. And thank you for being the whole 2 sessions or this session, and I hope you enjoy and you have more time to experience with this. And obviously, the good point about this is that from time to time we have much more data. Actually, this interface is going to include information from Solar Orbiter and from Parker Solar Prof. So this is in constant evolution. In the next months and years, we will have much more information. And this is what we call the multi-messenger solar physics, which is giving us a lot of new information to track the activity of the sun. The final aim is to be able to predict solar activity, but we are on the way for doing that. Thank you very much. That's all I have to say for today's session. I give the word to Manta. Thanks.
Okay, thank you very much, Santiago. It was again very interesting and very much involved. I'm sure people really learned a lot, and they've got interested in doing some hands-on session, trying themselves. So I'm sure they'll wait for your tutorials on Slack. And for everyone, please follow on Slack and put up your questions on Slack, because he has already provided you the tutorials for the first day on Slack. So I'm sure you can always discuss with us over there. Besides that, I have sent you also the link for the feedback form. So please go on the training program website, click on the link for the feedback and provide your feedbacks if you're not planning to attend the next 2 days training session. And if you're planning to attend the next 2 days as well, then please do it on the last day of the training program. That's on Friday. All right, besides this, I think I'll just say thank you very much again, Santiago. Thank you to everyone. And
my pleasure.
See you all tomorrow.
Thank you very much. Okay, see you tomorrow. Bye-bye.
Let's close the recording here.